Temporary access roads are carved into hillsides. Heavy machinery moves cautiously. Reach comes before structure.
Pier locations are marked across the valley. Each position follows precise alignment. Geometry is locked early. Rock face stabilization. Exposed rock faces are secured immediately. Loose material is cleared. Safety stabilizes progress. Water paths are redirected away from pits. Dry working conditions are maintained. Precision depends on control.
Foundation bases are leveled carefully. Rock surfaces are cleaned. Load transfer begins here.
Large steel reinforcement cages are assembled on site. Dimensions follow pier design exactly. Strength is shaped before concrete.
Steel cages are lowered into deep pits. Alignment is checked repeatedly. Accuracy defines longevity. Curing phase. Foundation concrete remains undisturbed. Time allows strength to develop. Patience protects scale. Foundation top finish. Foundation surfaces are trimmed to level. Anchor points are prepared. The base is complete. Tall formwork systems rise from foundations. Vertical lines define future height. The bridge prepares to climb.
Slipform system setup. Slipform mechanisms are installed around pier shafts. Continuous pouring becomes possible. Efficiency replaces repetition.
All right, start the flow. Bring it down slowly. Steady pressure now, keep that vibrator moving.
Sensors track pier alignment in real time. Corrections remain minimal. Precision governs ascent. The same process occurs across the valley. Multiple piers rise simultaneously. Rhythm defines progress. Strong valley winds move around rising piers. Structures remain stable. Design meets environment.
Form continuity check. Pier surfaces are inspected visually. No deviation appears. Consistency is critical.
Ready for deck support. Pier construction continues upward. Preparation begins for deck-level systems. The bridge prepares to span the void.
Slipform systems continue lifting pier shafts upward. Concrete rises without interruption. Height replaces ground presence.
Height-specific adjustments. Each pier responds differently to terrain height. Concrete rates are adjusted subtly. Uniformity meets variation.
Fresh concrete surfaces are smoothed uniformly. No joints interrupt continuity. Monolithic strength is visible.
Alignment verification. Laser instruments check pier positions across the valley. Tolerance remains extremely tight. Precision governs distance.
Final pier height reached. Tallest piers approach their final elevation. Movement slows intentionally. Completion nears.
Final pier sections are poured carefully. Edges and anchor zones are refined. Vertical construction peaks.
Pier. Pier crowns are trimmed and leveled. Bearing interfaces are prepared. The load path is defined.
Completed piers stand fully exposed. Wind flows around slender profiles. No visible deflection appears.
Temporary equipment removal. Slipform and lifting systems are dismantled. Piers stand independently. The valley feels taller.
Deck launching yard prep. Construction zones form on one side of the valley. Ground is leveled for steel assembly. The bridge shifts horizontal.
Massive steel deck segments arrive on site. Each piece follows a precise sequence. Assembly begins on land.
Bring it down slowly. Easy now. All right, hold it. Looks aligned.
Engineers verify straightness across multiple segments. Corrections remain minimal. Accuracy scales upward. A lightweight steel nose is attached to the front. It reduces cantilever forces. Engineering anticipates gravity. Support system installation. Sliding bearings and rollers are positioned. They will guide the deck forward. Motion is controlled before it begins. Bearings are installed atop pier crowns. They allow future movement and rotation. Flexibility is intentional. Clearances between deck path and piers are verified. Margins remain extremely tight. Nothing is left to chance.
Wind window selection. Launching schedules align with calm weather windows. Atmosphere becomes a construction variable. Nature is respected.
Launching systems are tested without load. Motors, rollers, and controls respond smoothly. Readiness is confirmed.
Deck alignment confirmed.
Orientation locked. Bring her down.
Structure secured.
Pier construction is complete. Deck launching becomes the focus. The viaduct prepares to cross the valley.
The lightweight launch nose extends ahead of the deck. It reduces cantilever forces. Gravity is managed carefully.
The deck advances toward the first pier top. Clearances appear minimal. Precision dominates scale. First pier crossing. The launch nose reaches the pier bearing. Loads transfer gradually. The system remains stable. The deck spans between two piers. Cantilever length increases temporarily. Engineering absorbs tension.
Wind conditions are observed continuously. Launching pauses if limits approach. Atmosphere dictates rhythm.
The deck resumes forward motion. Rollers rotate steadily. Progress feels deliberate. The deck reaches its longest unsupported reach. The valley drops away beneath. The moment is extreme.
Deflection remains within prediction. Confidence holds.
The launch nose meets the next pier. Bearings receive load smoothly. Alignment remains exact. As the deck settles, forces redistribute. Previous cantilever reduces. Balance returns. Segment by segment advance. Additional deck length moves forward. The process repeats methodically. Repetition builds certainty. The deck approaches the far side of the valley. Remaining distance shortens steadily. Completion approaches.
End support approach. The launch nose nears the final abutment. Clearances tighten again. Accuracy remains uncompromised.
Final support contact. The deck reaches its final support point. Loads settle into permanent bearings. The crossing is complete. Longitudinal alignment check. The full deck alignment is reviewed end to end. Straightness remains exact. Engineering holds across distance. Stone fire pit is constructed at the center of the platform. Walls are thick to contain heat. Airflow gaps are left intentionally.
Stack the kindling here, keep the logs separate. We need quick access.
Yes, sir, right away.
Look at the mortar here. It's failing.
You can tell just by looking?
After 40 years, yes. Hand me the mallet.
The defensive network is now visible. The Great Wall becomes a system, not just a barrier.
Watch your step.
Steady, heave. 1, 2.
Heave! Pull together now.
Heave! Ho!
Stone blocks are shaped roughly at the quarry site. Only basic tools are used. Precision comes later during placement.
Watch it, careful. Lower it down now. Steady.
Damaged stones are replaced with new blocks. Mortar fills weakened joints. Structural continuity is restored.
Brick kilns burn steadily with stacked fuel. Heat hardens bricks over time. Material quality improves.
Finished bricks are stacked and cooled. Color variation indicates firing differences. Selection is visual, not measured.
These new stones fit better than the old rubble.
Yes, but the foundation must be perfect if it is to last.
Drainage openings are added at regular intervals. Water escapes through small channels. Rain damage is reduced. Parapet sections receive additional reinforcement. Edges are thickened where erosion is strongest. Defensive height remains unchanged.
There's a slight sag in this section.
All right, I'll pry it up with the mallet. You apply pressure there.
Additional stone packing is added at the base of vulnerable slopes. Erosion protection increases. The wall anchors deeper into terrain.
Pull! All together now, pull!
Put the grain sacks in the third niche down.
All right, watch your step.
Endurance depends on maintenance.
Timber integrates with stone. Hybrid construction endure.
Close-up of drainage openings releasing rainwater downslope. Water control prevents structural damage. Design accounts for climate.